I would like to tell a little bit more about the standardization of EV charging. First of all, I would like to start with the big picture. Going from the left to the right, on the left side we see the technical regulations. Regulation drives technical standardization. Regulation both on worldwide, regional and national level. When we're talking about technical standards, then normally we have the international like ISO and IEC standardization committees that are actually responsible for drafting the standards, for writing the standards. Normally these international standards, they are adopted both on European and or regional level and also on national level. Because of standardization is rather slow, also other initiatives are there. Other initiatives driven from the industry with respect to the standardization on EV charging. When I'm talking about the other initiatives, I'm talking, for instance, about the CHAdeMO initiative. CHAdeMO is coming from Japan. It's originated from Japan, and it is only for DC chargers. The CHAdeMO standards, they include both safety requirements and interoperability requirements. Another initiative, for instance, is the charging initiative. The charging initiative is coming from Germany, and it includes both the AC and the DC charging. The CCS, the combined charging system, for instance, is coming from the charging initiative. Charging really promotes the interoperability, the interoperability that is between the charging station and between the electrical vehicle. Another initiative comes from France, which is called EV Ready. It is driven by the car manufacturer Renault in combination with the certification body ACEFA. ACEFA is taking care of the certification part of EV Ready, and EV Ready, in addition to the existing standards, EV Ready includes, for instance, additional requirements with respect to safety, additional requirements with respect to interoperability, reliability, but also requirements with respect to the installation of charging stations. And last but not least is the Open Charge Alliance that is originated from the Netherlands, and the Open Charge Alliance is in contradiction to the other initiatives. It is responsible, let's say, for the communication between the charging station and the backend. The OCR promotes open source standards, and one of the most important open source standards is OCPP, or the Open Charge Point Protocol. This is the communication between the charging station, as mentioned before, and the central management systems that are part of the charge operators. When we're looking at the overall picture of standards that DEKRA actually uses when we test the charging infrastructure, then we see a whole list of standards. Standards that are applicable to, for instance, the vehicle and the connectors part of the electrical vehicle. But also all kind of communication standards for the communication between the electrical vehicle and between the charging stations. The connectors, of course, that are part of the charging stations, and the communication, as mentioned before, between the charging stations and going to the back end. Also, with respect to the safety for the onboard chargers, there is a list of standards available. And for the physical connection between the charging stations and between the electrical vehicle, being the charging cables, also there are standards available. Also, when the standard is installed to the grid, then also some installation standards which applies, and also when feeding back energy to the grid, additional standards may apply. And last, of course, but not least, we have the safety standards, the standards that are applicable to the charging station itself, which is also a series of standards. With respect to the safety standards for the charging station itself, I would like to focus a bit more on it, because, as you can imagine, handling all the standards during this presentation, that would be too much. When I'm talking about safety standards for the charging station itself, I'm talking about the IEC EN 61851 series of standards. So what's in it when we are talking about the 61851 series of standards? It defines 4 different charging modes to start with. It includes all kind of basic safety requirements. Safety requirements for protection against electric shock, for instance. Safety requirements with respect to fire hazards, mechanical hazards, and also the resistance against environmental impacts. It has requirements for a so-called proximity detection. It has requirements for a so-called control pilot, which in fact is a sort of low-level communication between the charger and the electrical vehicle. But also for digital communication, also called a high-level communication between the electrical charger and the vehicle. And of course, the regulatory required EMC requirements are part of this standard. In the next slides, I will elaborate a little bit more about the different charging modes that are applicable, also about the proximity detection, the control pilot, and the digital communication. When I'm talking about the charging modes, in total there are 4 modes defined. First of all, charging mode number 1. Charging mode 1 depicts AC charging at normal mains outlets. Meaning this is the most simple basic form of charging. There are no protection devices inside the charging cable, for instance. It requires an RCD, a residual current detective device, as an additional safety device to be part of the domestic installation. With this form of charging, it is not possible to feed back any energy back to the grid. So it's not possible to go to have an energy transfer from the electrical vehicle into the grid system. The charging power is limited. It is limited to maximum 16 amps, so for the domestic installation. This also means that it is prohibited in some countries. It is prohibited because some countries do have older installations where there is no RCD present, so you would fully rely on the installation at home. There is a communication. No, not in this system. There is no low-level communication and no high-level communication. There is an interlock. Yes, there is an interlock with this system, but the interlock is only at the vehicle side, which means that once charging, you cannot disconnect the cable from the vehicle. The next charging mode is the mode 2. This is also AC charging, but AC charging also from normal mains outlets, but it can also be charged from 3-phase AC outlets, but domestic outlets, normally the domestic and the industrial ones. This charging mode has a so-called in-cable control box that has additional safety features. Meaning this box, as you can see on the right side of the picture, it includes, for instance, the residual current detection device. It also includes a proximity sensor, and it includes the low-level communication by means of a control pilot. So it has a form of communication, the communication between the cable box and between the electrical vehicle. Charging power is limited. It is limited to maximum 32 amps on a 3-phase system. But also here, for some countries, there's a limitation when using this kind of, when using mode 2 charging, there's also a limitation to a maximum of 16 amp. So is there a communication? Yes, there is a communication from the box to the vehicle, but only low-level communication, no digital form of communication. There's also an interlock, similar as for mode 1, only an interlock which is part of the vehicle. When we are talking about the charging mode 3, then we are talking about charging, AC charging at public sites. So this is what we see actually when we charge our electrical vehicles, for instance, in garage or at parking lots. Here, the safety equipment is permanently part of the charging station itself, meaning there is no in-cable control box required. The cable and the plug, it permits unsupervised charging because there's both an interlock at the charging station and an interlock at the vehicle side, meaning that during charging it is not possible to disconnect the cable from the vehicle nor from the charging station. So charging can be unsupervised. With this system, it is possible to do feedback of energy, feedback to the grid. But most of the AC charging stations, they don't have that facility yet because beside of having, let's say, the interface, the technical interface over there, it also requires high-level communication. And most AC, Mode 3 AC charging stations, they do not support this high-level communication. And last but not least, of course, is the Mode 4 charging. The Mode 4 charging is not for AC charging, but for DC charging. So for Mode 4, we are talking about really high power, more high power charging. For Mode 4 charging, digital high-level communication is required. The electrical vehicle takes the lead in Mode 4 charging, which means that they communicate let's say, charging parameters back to the charging station. And the charging system itself, so the charging station itself, it can manage various charging currents and charging voltage. So it actually can need to adapt, and it can adapt to the needs of the electrical vehicle which is connected for charging. When we are talking about, for instance, the CCS-DC system, you can see at the right hand of the picture, you can see a picture of the CCS combo plug, which supports both AC and DC inside one plug. In the middle, we see a picture of the CHAdeMO plug, which only supports the DC as previously discussed about. DC charging can go up to several hundreds of kilowatts at the moment, and every time we see an increase. We see an increase in even more power every time. Proximity contact. The standard also has a requirement regarding proximity contacts. If we're looking at the picture, there we see a type 2 charging plug, an AC type 2 charging plug. We see two contacts on the top of the picture. One of the contacts is the proximity pin. The proximity pin has, in fact, two functions. The main function of the proximity pin is that it can detect whether the charging cable is correctly connected between the charger at one side and between the vehicle at the other side. Once the charging cable is connected and cannot be taken loose again, then the electrical vehicle can take the appropriate actions, such as, for instance, activating the onboard charger, but also, for instance, deactivating the drive, so that it's not possible once you charge your car that you can drive away with the car. It also has an optional function, and the optional function is called the so-called resistance coding function. You can imagine that not in all cases, because this plug supports charging currents up to 63 amps for 3 phases, that it cannot, that sometimes when you use, let's say, a smaller cable with less cross-section, then the current cannot be that high. This is why resistance coding is used. Resistance coding is used both in the connector and plug, so that both the charging station and the electrical vehicle are aware about the maximum current that can be guided through the charging cable itself. The next slide is about the control pilot. The control pilot is the other pin which is on the right hand of the picture. It's a very important function which is used to monitor and to control the interaction between the electrical vehicle and the charger. It is mandatory. A control pilot is also called the low-level communication. It is mandatory for mode 1, mandatory for mode 2, mode 3, and mode 4 charging. The control pilot wire is a supplementary conductor that actually and physically connects the charging station and the vehicle with each other. It includes mandatory functions such as the monitoring of the protective earth conduction, so whether there is continuity of protective earthing, also verification whether the vehicle is properly connected or not. It also takes care about energizing the system and de-energizing the system. So once the control pilot is connected, you can energize the system. And if the control pilot is open, then the system needs to be de-energized immediately. And it is also responsible for the selection of the charging rate. It does that through a so-called pulse width modulation. And the pulse width modulation by changing the pulse width, the charging station communicates to the electrical vehicle the amount of current available for charging. When we are talking about the digital communication, then that's definitely mandatory for the mode 4, so for DC charging. It allows the electrical vehicle to control the charger. As mentioned before, the electrical vehicle takes the lead in the communication. Also, additional communication standards in that situation apply. For instance, the very important ISO 15118 series. For the CCS system, the communication takes place via so-called power line communication. So it is a power line communication that communicates over the control pilot line. And for CHAdeMO, it takes place via, for instance, a CAN bus. It is very important for both the interoperability and the safety. And it includes many functions. Some examples, for instance, are, as mentioned before, exchanging of the charging parameters. So to what voltage the battery of the electrical vehicle can be charged. For instance, to what current, what is the maximum current that it can be needed to be charged. But also to exchange information, for instance, on the state of charge of the battery. But it can also be used for, let's say, payment details, for exchanging payment details, and also for shutdown, normal shutdown, but also in case of an emergency, for instance, an emergency shutdown of the system. In the next part, I would like to tell a little bit more on how we test EV charging stations at DEKRA. When we're looking at the picture, then we actually see the test system we use for that one. The test system at the picture, it simulates the electrical vehicle charging controller. The test system is connected to a load, and the load simulates the electrical vehicle battery. So the test system in combination with the load is the simulation of the electrical vehicle. The charging station during tests will be connected to the test system, and in that way we can perform safety testing. In that way we can perform all kinds of charging performance testing, interoperability testing, conformance testing, but it is also used for EMC testing, for durability and all kinds of performance testing, even at all kinds of extreme conditions, for instance introducing single fault conditions. EV charging stations challenges. When we're looking at the current situation, then we can say, okay, the existing regulations and the current set of safety standards for charging stations, the electrical vehicles, and the connection between the charging station and the electrical vehicles, they support a safe charging infrastructure. So all the standards we have seen, let's say on one of the first slides, they are used for testing and for investigation and developing the charging infrastructure, and they support a safe charging infrastructure. We can also state that charging stations that are tested and in compliance with the current set of the safety standards, that they are safe. And that charging stations and electrical vehicles that are tested and comply with the communication standards as mentioned on the first slides, like for instance the ISO 15118, that they provide a higher degree of interoperability. So it seems that there are no issues or problems anymore. This is not fully correct, because actually in the field we still see some problems. I will give you some examples of that. Some examples that we currently experience in the field with respect to, for instance, the safety, the interoperability and the installation of the charging stations. When we start, for instance, with the part on the safety, then we have this requirement, this prerequisite requirement of a residual current device that should be part of the installation, especially for the home charges. But as we all know, also within the Netherlands, we have some older type of installations where there is no RCD part of the installation, which means that the installation needs to be carried out actually by skilled persons who make sure that an RCD is part of the installation, because it's very important for the additional safety protection. Another issue we see in the market is, for instance, the 6 milliamp DC leakage. When we're charging at 3 phases, when an electrical vehicle charges at 3 phases, then the converter inside the electrical vehicle, when it rectifies 3 phases into a DC to charge the battery of the electrical vehicle, it also creates a nasty effect which is called DC leakage currents. And this DC leakage current, when they go above 6 milliamp, they have the effect that they can turn the RCDs, so the additional protection, the residual current devices, that they can be turned blind, meaning that they cannot operate anymore. So, and additionally, detection is required for the 6 milliamp detection. What we also do not know with respect to safety, for instance, is what would be the crash impact on charging stations. What would be the effect when there are crashes? There's not much information about it at the moment. Also with respect to fire safety, multiple charging stations together on a parking lot or in a garage. Also with respect to fire safety, there can be some questions. And also issues with respect to incident management. What is the knowledge? What is the exact knowledge, for instance, about and the training of the first and the second responders? If there's an incident and they have to access, let's say, especially the more dangerous high-power charging stations. Just a few examples regarding the safety we currently see in the field, and that definitely would require attention. Also, with respect to interoperability, we still see problems. Many due to, for instance, timing problems. Timing problems because of wrong interpretations of the standards. Timing problems because of legacy vehicles. So let's say the little bit older type of electrical vehicles that want to charge on the new type of charging stations. There we also can see problems. Problems, for instance, with noise and distortion that would have a negative influence on the charging process. Or, for instance, when we have to deal with load management, so connecting many multiple cars, let's say, to charging stations that are all connected to the same phase, which could cause, let's say, long waiting times on charging. This especially goes for AC charging, of course. And when we are talking about installation or maintenance of charging stations, then for instance, installation of charging stations, it's very important that skilled persons carry out that installation. So what are the skills for the people working on charging stations? Most of the countries, they don't have follow-up inspections for charging stations or maintenance requirements for charging stations. So what happens over the years if the charging stations stay in the fields? What happens if, especially for home chargers, amateurs, they perform the installation by themselves and do not implement, for instance, an RCD, or even worse, that they modify the charging station and they use inferior or parts or components. What we, for instance, have seen in the market is a misuse of a charging station where there was a construction site where actually a charging station was tricked to output power to the construction site where houses were built. This, of course, is misuse of a charging station and can be very dangerous.
Thanks for the overview, André. I think it's a very comprehensive overview with a lot of, let's say, valuable and important information. I recognize the site of DEKRA in Arnhem that you were showing on the site, and I know that's quite a unique facility. Can you tell a little bit more, let's say, what is the uniqueness of that facility related to testing of charging stations?
Yes, Vincent, of course. I think it's the test system we have at DEKRA Arnhem facilities is very unique. Not only because it can be used, let's say, for safety testing, the interoperability testing, and for the performance testing, but it is also a unique test system because it supports not only, let's say, the IEC or the regulatory standards, but it also supports all the initiatives like, for instance, CHAdeMO, like CHARIN, like EV Ready. So it's also very important for those purposes. And this test system that we currently have in Arnhem, it can also be, it also has a multiple configuration, which means that it can also be configured not simulating an electrical vehicle, but simulating a charging station, which means that the same system can also be used to test the vehicle instead of testing the charging stations. At the moment, we can test up to 360 kilowatt with the system, but it easily can be extended to 720 kilowatt, which means that we currently can handle almost all the high power charging systems that are on the market. And last but not least, it is a fully automated system, which means that when we use this system for testing, that definitely decrease test time. If we would have to do the testing in another way, all those tests that need to be run according to the standards, that would take a lot of time, and it would be very costly as well, of course. And this automated system definitely reduces testing time, and it also can be used for analyzing problems if problems occurs, because we actually can follow the complete communication that goes on between the charger and between the electrical vehicle.
That's indeed a unique setup, really end-to-end testing with all the possibilities, including all the industry standards and the industry standards regulations there.
Yeah.
Last question, any final advice for the manufacturers in, let's say, terms of development for charging stations related to testing?
I think in one of my last slides I mentioned challenges. There are continuously challenges because, as you also mentioned during the introduction, it's a fast-moving market with a lot of technology. Technology constantly changes, and the manufacturers, they have to deal with it. So they have to focus on all the changes that are in the market, and whatever they can take into account during testing already or during pre-testing, that would be really helpful, I would say. And this is also a challenge for the manufacturers, of course, because they not only have to follow what's going on in standardization, what's going on in the initiatives, a lot of new requirements they have to comply with, but it's also a challenge, of course, for them because they want, in the end, they not only want to sell a safe and interoperable system, but also against a competitive price, of course. And it's a continuous challenge to my point of view. And we from DEKRA side on, we can support them with a lot of, at least with the safety testing, with interoperability testing, so they bring safe and interoperable systems to the market.
I think that's a very good advice. So thank you very much for watching. We hope you enjoyed this webinar. Please keep an eye on the social media channels and DEKRA websites, because we will be issuing more webinars of this particular type. Not about e-mobility, there will become more e-mobility webinars as well, but all kinds of different topics there. Thank you very much for your attention and see you next time.